under the umbrella of dynamic programming. And this is really why I think the topic has such a bad reputation for being very difficult, because the problems range so much, right? It looks like these problems are totally different, and there may not be any underlying mechanic that we can use to tackle all of them. But the short answer is we really can if we have the correct way of thinking about these problems. That being said, let's go over the overall format of this course. In this course, I think our key to victory is going to be to really visualize all of these algorithms, right? So we're going to spend a lot of time drawing things on the whiteboard, as well as visualizing things with that to make sure we're really happy it's a program. I think discovering these two is going to be about tabulation. And don't sweat it if you have no idea what those two terms refer to. These soon clear. What I want to do is write a function fib of n that takes in a number as an argument, and I need to return the nth number of the Fibonacci sequence. And the next number of the sequence, we can just sum 3, 5, 8, 7. Did we actually calculate that 13? We need to return the answer 13, right? Because the seventh Fibonacci number is 13, 7, so on. For 13, so very, very classic function here. And to really get us going for what we do later on in the lesson, I'm going to require us to solve this one recursively, right? It's really going to be at the heart of the topic for today. So why don't we kick things off by quickly implementing the classic recursive implementation of a Fibonacci function. You've probably written this function a few times in your programming career, usually one of the earliest examples of recursion that we face. So we'll just lay out the classic implementation here. So I want to take in a number n, and I want to return the nth number of the Fibonacci sequence. Like we expect, the base case is just about the first two numbers of the sequence. In other words, if I'm given some n that's less than or equal to 2, then what I should do is just return 1. And I'm writing this because, hey, the first two numbers of the Fibonacci sequence are exactly 1. But in the recursive case, in general, what I can do is just return the sum of the Fibonacci number right before, the one I'm asking for, as well as the Fibonacci number 2 before, the one I'm asking for, right? Again, the kind of baked-in recursive nature of Fibonacci is to calculate some Fibonacci number, you can take the sum of the previous two numbers in the sequence, right? Now, of course, we should test our code for some correctness. And 8, so let's give this a go. I'll run implementation of larger number, something reasonable fine, right? I get 8, 13, and 21, but the fourth call is actually still running, right? My program actually hasn't finished. Go ahead for some efficiency. We had drawing it on lectures. Asking on to us on see it. So one is we return tree. We get the full number is in turn to your node is base case. Let's say I look at some node, in particular this base case node of 2, right? I know that this node is a base case, so it's going to return the value of 1 according to my base case. When we say return, that really just means return to your caller, right? Or return to your parent. So this node of 2 is going to return 1 to its parent of 3. In the same way, this node on the right-hand side of 1 is also base case. It too will return 1. Both of those values that are returning, they go back to the parent of 3, and 3 is actually going to add those two values up. 1 plus 1 is 2. And this makes a lot of sense because we know that the third Fibonacci number is 2. So we can continue this process. Look at this node over here. This is also base case, so it returns 1. And now the parent node of 4 is going to sum up both of its children values. 2 plus 1 is 3. And that makes sense in itself because the fourth Fibonacci number is 3. So you probably get the picture now. Let's speed things up. For all of these base cases, I know that they're going to return 1 to their parent. And for all parent nodes that have both of their children ready, that is both of their children returned, they're just going to add up those values. And this process just continues all the way up the tree, right? Just adding our left and right children together makes a lot of sense to understand. And that for us, it variation behaves to calculate throughout on every return complexity of our recursive call are different function calls. The space complexity, well, you may have heard in the past that when we analyze the space complexity of our recursive function, I had to put a little warm up. Let's say that I gave you this foo function. Notice that it's different from our fib function, right? It's similar in that it's recursive. This function is kind of arbitrary. It actually doesn't calculate or solve any particular problem. So if I wanted to visualize how this foo function behaves, let's draw it out. Let's say I initially call at the top level foo of 5. I know 5 is not a base case, so it's going to call upon n minus 1, or it's going to call upon 4. 4 calls 3, 3 calls 2, 2 calls 1, and then here we've actually bottomed out at a base case. If I look at the number of calls I made, I basically made exactly 5 function calls, which makes sense because in terms of our base case, right, we stop once we hit a number less than or equal to 1, and in every recursive step, we just subtract 1 from our current value of n. So overall, I have 5 calls here, but if I generalize that for any arbitrary input, I know that in the long run, I'm going to have about n different function calls recursively. And so for that reason, the time complexity of this is really just O of n time, right? I have to evaluate O of n different function calls. And while we're at it, why don't we take a look at the space complexity? Well, you may have heard in the past that when we analyze the space complexity of our recursive functions, we should include any of the additional stack space that our function calls take up, right? When we make a recursive call, we add that to the call stack, and those must be tracked by our computer. And so since we have about 5 or n different function calls added to the stack before we hit our base case, we can say that the space complexity of this code is of the calls have a time about our calls. You may be able to see the reason I wanted to O of n minus 1, the other did minus 2 for both of these functions. Steps over here, and they both do an n minus 2. When it's did function, the metric select ran find before, right? And 3 is top level. For example, here in yellow, I rewind things a bit. If I look at then 8 implies that. So I know no matter what, whenever we call some top level argument for dib, we know that we're going to have one node at the top level, but to get the number of nodes on the next level, I'll just multiply that by 2, and the level after that would be top level. level, there's 1 node here. On the next level, there's 2 nodes. On the next level, there's 4 nodes, then 8 nodes, then 16 nodes. See the pattern? So let's try to generalize that. So I know no matter what, whenever we call some top level argument for dib, we know that we're going to have 1 node at the top level, but to get the number of nodes on the next level, I'll just multiply that by 2. And the level after that would also multiply by 2, and multiply 2 again for the levels after that. And I do this a total of n different times, right? Because I know that the height of the tree, or the number of levels in this tree, is exactly n. And so what conclusion can we make over here? We're basically saying that to get the total number of nodes, or the total number of calls our recursive function would make, we would just take the number 2 and multiply it by itself about n times over. And that is really the definition of an exponent, right? This is the same as 2 to the nth power. And so we can say that this tree structure, or this recursive function, has a 2 to the n time complexity. Awesome. So we identified this dib function as having a 2 to the n time complexity, but what do we know about...
Alright, so in today's video we are going to discuss logarithms and time complexities. So this is something that confused me for a very long time, and if this is something you're already familiar with, you don't really need to watch this, you probably already know it. But there's certain instances when we're deducing complexities with things like binary search we'll see, things like merge sort, quicksort, where we see a logarithm appear in the complexity, and my
about the space complexity over here. I think a common mistake I've seen people make is kind of automatically assume that
goal by the end of this video, I want you to have a full and intuitive understanding of what a logarithm means and why it is useful for us and the question it asks us when we are declaring a complexity using a logarithm. So let's first investigate what a logarithm is and the fundamental question that a logarithm asks us. So I want you to get, again, the intuitive understanding of this. A logarithm asks us a question. So I want you to look at this. Log base 2 of 8. So what does this logarithm ask us? It asks the base of 2, what do I need to power the base of 2 by to get the number in the parentheses, 8? Well, that answer is 3. So why is it 3? Let's look at what we're actually doing. So do you see how we're doing 3 divisions until we get down to 1? We go from 8 to 4, that's 1 cutting in half. We go from 4 to 2, that's cutting in half again. And then we go from 2 to 1. And do you see, we cut in half 3 times. This 3 looks familiar. That's the 3.
Oh. Just तिम्रो बेस कन्डिसन आउनलाई हैन बेस कन्डिसन आउनलाई त्यो फंक्सन तिमीले कतिचोटि कल गरेर चाहिँ यसको बिल्कुल हाइट चाहिँ लग एन छ के बुझ्यो जस्तो यस्तो हैन के log n एकदम नन-लिनियर भयो भने कारणले the last one. Logic हो L log of n चाहिँ O of n हुनु भनेको चाहिँ के भने चाहिँ तिम्रो यो ट्री ट्राभर्सलको टोटल एरिया हुन्छ नि वर्स्ट केसमा चाहिँ O n equals to n log n हुन्छ भनेर area of tree भनेको breadth and height हो breadth and height हो होइन भनेको O of n equals to tree को height into tree को width हो होइन tree को width भनेको त तिम्रो height भनेको त फिबोनाची छ रे f of n minus 1 plus f of n minus 2 n minus fn छ भने यसको बेस कन्डिसन त n equals to 1 हुँदासम्म आउँछ है n बाट भनेपछि एक एकले घटिरहेछ भने n बाट एक एकले घट्दै 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 0 सम्म अथवा n equals to 1 हुँदा n equals to 2 भनेर देख्छ e of n छैन height ट्रेक भइन्छ यसको बेस कति हुन्छ प्रत्येकमा 2 2 छ नि रेट अफ ग्रोथ ग्रोइङ कति छ भन्दाखेरि 2 को पावर छैन हाइट इन्टु बेसको प्रोडक्ट हो प्रत्येक स्टेपमा 2 2 ले ग्रो भइरहेछ भने n वटा एलिमेन्ट n वटा स्टेप पार गर्दा यसको विथ कति हुन्छ पहिलो स्टेपमा 2 थियो त्यति छ है यो चाहिँ n equals to n हुँदाखेरि गर्दै 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 गरे के भयो n equals to 1 भयो यतिवटा स्टेप पार गर्दा यसको विथ कति हुन्छ 2 को पावर n छ हाइट n छ भनेपछि O of n 2 को पावर n म्याटर गर्दैन 2 को पावर n म्याक्सिमम भ्यालु ठिक भइहाल्यो अर्को म्याटर गरेन जसले यसले उहाँसँग बेच्ने अर्को कुरा चाहिँ जस्तो तिम्रो f of n छ होइन अनि तिमी f of n by 2 plus f of n by 4 गर्ने फर्स्ट केस त ट्री को हाइट त्यसले डिटर्माइन गर्छ त्यसले डिटर्माइन भयो यसरी हिँडिरहेछ यतापट्टि छ यो ट्री को समस्या तर यो चाहिँ यहाँसम्म गएर यो ट्री को हाइट कति हो लगभग n होइन हाइट के लगभग कति गर्छ यहाँ लगभग n into 2 to the power n लगभग प्रत्येक केसमा दुईटा डिवाइड गर्दै हाफ गर्दै गरिरहेछ भने कति लगभग individual array element है element twice आउँदै आउँदैन र यो बिटको twice आउँछ यो twice आउँछ यसमा आउँदैन यसलाई मैले यस्तो गरेँ हैन एउटा यसले यस्तो गर्यो यसलाई निकाल्नु दियो यहाँ पनि गर्यो भनेपछि n त हुने कुरै भएन यसमा के हुन्छ यो रिपिटेटिङ कुरा भयो भने रिपिटेटिङ कुरा जस्तो n + 2 छ हैन 8 हुन्छ टाढा हुन्छ त्यही कुरा डबल एप्लाई गर्छ हुन्छ f of n minus 1 plus f of n minus 2 छ हैन यो भनेको f of n minus 1 plus f of n minus 1 plus f of n minus 2 log f of n minus 1 n minus 3 log f of n minus 1 plus f of n minus 4 plus f of n minus 5 again log n minus 1 plus f of n minus 2 f of n minus 4 यो भनेको log f of n minus 5 plus f of n minus 6 plus something again प्रत्येकको अगाडि के आइरहेछ n आइरहेछ
we just got there. So does that ring a bell? So the thing is, that's why a log base 2 is considered cutting in half. We're
just again, right?
You're performing divisions by 2, divisions by 2. So a logarithm is a expression of a having when it is under the base of 2. In computer science, we most often use the log base 2. In fact, we almost always use log base 2. But in general mathematics, you're going to see log base 10 most of the time, and this is what you'll see. You'll see nothing. So when you're doing calculus, you're always going to assume a log base of 10. This is just the general thing with normal mathematics. But when you're in computer science, you'll also see the 2 is not there. So the thing is, it's always the implied context that the base is going to exist in. So when we're doing calculus, we'll just assume it's log base 10. When we're doing computer science, we'll assume it is log base 2. And we're going to see why that is the case most of the time. Anyway, let's look at the second example. Now we're looking at log base 10. We're looking at log base 10, and what does this ask me? I don't want you to look at this. What does that ask me? That asks me, my base is 10. What do I need to power 10 by to get the value 100? Well, the power I need to power 10 by to get the value 100 it's going to be 2. So 10 squared is going to be 100. So the thing is, what a logarithm is asking is it's asking, are we going to be having? Are we going to be tenthing? It's all about powers and calculating exponential quantities. So when we're doing a log base 2, we want to see how many times did I multiply or divide by 2 to get to a certain value. This is like the intuition behind it. So this is what it would look like for the having for the log base of 2. So for the log base of 10, this is what it would look like. So do you see how we just tenth 2 times? We just cut tenths twice. We cut halves 3 times. Hence the 3, hence the 2. This is what a logarithm is all about. Remember, it's all about what do we want to power the base by to get the number in the parentheses. So where does this appear in computer science and why do we care about this? So let's investigate further. So here is a case where our logarithmic time complexity is going to be familiar to us. When we're dealing with any binary structure like a binary tree of sorts, so we're going to have at least 1 plus the floor of log 9 levels if we have n nodes. N is 9 in this case. If we actually do the math, and remember, we're using log base 2 because in computer science we always use log base 2 implicitly. We just assume it's going to be log base 2. What we're going to have is the log base 2 of 9 is going to be 3.17, and these little brackets you see, those like brackets are the floor symbol, so it means we just truncate the decimal place. We just truncate the decimal place, and we're going to have 1 plus 3, so we have to have at least 4 levels. So this is accurate. We have 1, 2, 3, 4. 4 levels. We have approximately log n levels. So if we took the asymptotic complexity or the asymptotic behavior of a traversal of the height, we're going to be performing logarithmic approximately log n levels. So if we took the asymptotic complexity or the asymptotic behavior of a traversal of the height, we're going to be performing logarithmic work when we are traversing the height of a binary structure like this. If it is balanced, at least. If it is skewed to the right, then we're going to be doing linear time work, but that's for another day. We're going to assume we have a balanced tree structure. Now let's look at other implications of where we use logarithms, and we'll notice them in time complexities. All right, so we have an array. So I want to ask you the question, how many times can we cut this in half? And let me give you a little help. This is all you need to know how many times you can cut this in half until we get to one item. So why is that? So why don't we start cutting it down in half? So let's go one level down and cut it in half. Okay, so now we have cut the input once. We've split it in half once, and now let's split these guys in half. Okay, so now we see we are 2 levels deep. So how much farther can we go? Let's split these guys and split the original input. So maybe we could use this. Maybe this was a helpful hint I gave you. So if we take the log of this, and again, always base 2 when we're dealing with complexities implicitly. So if we take log base 2 of 8, what is the answer to that? What am I asking? What do I need to power 2 by to get 8? And we can see here, this is how we know how many levels we can split our input. This is where the logarithm came from. So is this familiar? Does this look familiar? So the thing is, merge sort and quick sort run in n log n time. When we don't have special knowledge about a certain set of unsorted data, the best we can do is n log n time with merge sort, quick sort, or the fast sorting algorithms. So why is this? In the recursion, we're going to be able to split the inputs for merge sorts up to log n levels of work. As you see all the levels of work. You see we can split 3 times, which is log of n. So on each of those levels of work, we do about linear work. Now the recurrence relation and the actual complexity gets a lot more fine-tuned than that in terms of like the exact operations we do. But this is a general overview of where that comes from, where that n log n comes from. We have log n levels of work, and we're going to be doing a certain amount of work for each level. So that's why we do a multiplication against the logarithm. So that's where that comes from. So this is what merge sort and quick sort will do when they're partitioning the array. In merge sort's case, we drill down to base cases, and then we come back upwards with a sorted array. Now let's look at another example where logarithms show up. All right, so now here's another example. We have a sorted array with the indices numbered. We automatically know we can do binary search. We have the invariance that if we cut the array in half at any point, we will have a sorted array in both of our hands. So what we can do is here, we can set our bounds, and let's do a binary search and see how many times we can perform a halving of the search space at maximum. Okay, so we just set our bounds, and our midpoint is going to be right there. We see we hit 4. Is 4 the value 1 that we're searching for? It's not. We overshot it. Since we overshot it, we need to look to the left. We want to go lower in value. So what we're going to do is narrow the bounds. Okay, so let's take note of that. So we were able to narrow our bounds 1 time. So now let's find our new midpoint. Is 2 the number we're looking for? So the thing is, 2 is not the number we're looking for, so we need to keep going left. And we found the item 1. So we performed a total of 2 halving operations to find our item k.
that the space complexity of a recursive
So we have seen that A with some this reduction is given. No, the way in which we have to analyze the time complexity is very much different from the way we used for iterative functions. The reason is there is nothing to count here. That is why we write something called as recursive functions, and then we try to analyze them. So how do we write it is, in order to solve a of n, let us assume that time taken is t of n. Okay, now how is that time split up is, first of all we are trying to do some comparison here, something if condition. Let us assume that for if condition time taken is some constant, and then we are going to find out on t of n, this a on n by 2 and again a on n by 2, and then we are summing up. So there is some constant time involved for this if condition and for this addition, therefore some constant time plus we are calling a of n by 2 2 times, which means 2 times, if for t of a of n time taken is t of n, then for a of n by 2 time taken will be t of n by 2. Okay, so this is how we should write the recursive functions, and then we should try solving these recursive functions. So one way how we could solve the recursive function is, I'll take an example and I'll show you. There are various ways, I'll take some examples and I'll show you this. See, one way of solving this function is, assume that the function is like this: a of n, if n minus t of a of n is t of n, then that time is actually, so the problem will be t time using 1 taken to be t called. This method is somewhat slow. Let me solve it. So t of n equal to 1 plus t of n minus 1, right? Then what will be t of n minus 1? If I substitute in place of t is 2, then I get n minus and equation 3. Now of n equal to minus 1, I'm minus 2. In place of n minus 2, I'm going to, then what is 3? We can go of n minus k. Okay, so this
statement. This is what you are going to get finally. So if k, then we are going to get k plus t, t of n minus k. Then where do you want to stop it? When are you going to stop it? So see the algorithm when it is going to stop. So this equation t of n equal to 1 plus t of n by 2
t of n equal to 1 plus t of n minus 1 is valid only when n is greater than 1, isn't it? So this is valid when n is greater than 1. Then what happens if n becomes 1? N is going to start from a very large number and it is going to gradually decrease. According to this algorithm, it is going to gradually decrease, and at some point it is going to reach 1. Therefore, whenever it reaches 1, we are simply going to stop, which means we'll just do the comparison, this one, and whenever it is 1, we are going to stop, right? So this is called anchor condition or base condition or stopping condition, which is going to stop the recursion. Now, this one will stop. If you want to eliminate it, then you should get t of 1 here. If I have to get t of 1 here, then n minus k has to become 1, which means n minus k has to become 1. Then for what value of n minus k will become 1? Then for a value of n equal to, or for what value of k, this n minus k will become 1. For k equal to n minus 1, this value will become 1, which means in place of k, I am going to write n minus 1. So on, in place of k, I am going to write n minus 1 plus t of n minus 1. Then what do we get? N minus 1 plus t of 1, that equal to t of 1, we already know that it is 1. Therefore, it is n minus 1 plus 1, that equal to n. Therefore, t of n equal to n. You can even write it as order of n. This is the answer. This is called back substitution. So just recollect what we have seen. Now, if there is an algorithm which depends on the input size of n, then I am writing it in terms of input size of n minus 1. Then I am using a method. No, after writing this recursive equation, how did I write the recursive equation? Let us assume that time taken to solve an instance or a problem of input n is t of n. Then how is that time split up? It is actually the time taken to compare, which means some constant time, and then to return, which is some constant time, plus time taken to solve n minus 1, t of n minus 1, right? And you should even find out the base condition. Why? Because that is where the function is going to stop. Base condition is when n equal to, let us say 1. When n equal to 1, it is going to return 1, right? Then what did I do? I kept on back substituting. In place of t of n minus 1, I substitute this. In place of t of n minus 2, I substitute this. So we could go on like this, and finally I got the answer to be n. So which is also order of n. Okay, we shall see one more example. Let's see one more example for back substitution. Let us say some algorithm is given, and after converting it to recursive equation, later when we see the algorithms, I'll even show you how to convert it to recursive equation. But for now, just consider that already recursive equation is given, and the recursive equation is like this. Time taken to solve a problem of n instances is, just assume that some n plus t of n minus 1, which means time taken to solve a problem
n square.
on n instances is n time taken plus time taken to solve remaining n minus 1 elements. I mean the algorithm is run on n minus 1 elements. Let us say this is when n is greater than 1. and that equal to 1 or some constant time. C or constant, it doesn't make any difference. And n when n plus t of n minus 1, which means time taken to solve a problem on n instances is n time taken plus time taken to solve remaining n minus 1 elements. I mean the algorithm is run on n minus 1 elements. Let us say this is when 1 elements. N time taken plus time taken to solve remaining n minus 1 elements. I mean the algorithm is run on n minus 1 elements. Let us say this is when n is greater than 1 and that equal to 1 or some constant time. C or constant, it doesn't make any difference. And n when n is equal to 1. Okay, so how to solve it is again the same method. So if I have to substitute this, I should know what is the value of t of n minus 1. In order to find out t of n minus 1, in place of n you substitute n minus 1. So what do I get? In place of n, if I substitute n minus 1 in place of n, then I am going to get, in sense it is, and this is equation over number. Equation number already, let me write off, equal to, in place of n minus 1, this one, right? That equal to, in place of n minus plus, writing it in a sequence. Now what when is it going to stop is, we have to eliminate this t completely. I have to write t of t by using which eliminate. This entire term has to be 1. If this entire term has to be 1, then what should be the value of k? That is what I wanted. Then n minus k minus is 1 equal to 1. That implies k equal to n minus 2. So for a value of k equal to n minus 2, I'll get here as t of 1 and I could stop it. Therefore I'm going to substitute k equal to n minus 2 here. Then what happens? N plus n minus 1 plus n minus 2 plus so on plus, in terms of this k, I'm going to substitute 1 plus n plus, and this can even be written as, always remember, whenever I have a polynomial of function of like this, n plus k to the power m, then what is the most significant term in this? N power m. So don't worry about the constants. Then we could, it is n square. Therefore I could always, or that also we could, if worth noting. So in order to solve a problem with n inputs, the time taken will reduce amount size and amount of constant level would break, and amount a break, and of C. Now how much amount of work is done at this level? Taking it into t of n by 8 and t of n by 8. And again, if I do a constant work, so at every level how much work is done and how long are we going to go. So we are definitely going to stop it whenever we reach t of 1, right? T of 1. Now how much work is done at this level? C work. How much work is done, total work, amount of work done in this level? 2, which is 4 into C. Now, so at the last level, how much work is done? C. When it is t of n by 8, the work done is 8C, isn't it? At the last level, what is it? How can you write it in n by something? If I have to write t of n in n by something, how can I write it? T of 1 is nothing but t of n by n, right? So when it is t of n by 8, the total work done is 8C. When it is t of n by 4, the total work done is 4C. When it is t of n by n, the total work done at this level will be nc, right? So if I add up the total work done, what do we get is c plus 2c plus 4c. C as n, just by assuming that n is a power of 2, result, or it is not going to change anything. Answer is, therefore assuming that this as for k of term for total formula common difference k plus 1 minus 1. So we have already seen that for it is complexity 2. Complexity, for example, if I write it as order of n. So that is the time complexity taken by this, we got from this equation. Okay. So we shall see one more example using this recursion tree.
Like I said, new equation diagram. In particular on that, n is greater than equals to 1. This I am. ఇవాళకి ఉంది t 1 to the power login plus पहले पूरा ये करा था इसके वैल्यू का 3 था 1 plus 2 a r to the power n minus 1 to the power login नहीं कर दिया ये बाबा 2 to the power log n1 equal to 0 and 2 to the power log n1 equal y minus log of n equals to log of y divided by 2. 2 to the power n log n1 equals to single neighbor, isn't it? इसलिए मुझे प्रोग्रामिंग दोस्तों प्रोडक्ट ट्रीज तो yeah, t of n by 2 into 2. So this is the condition, right? So what does it do? So t of n by 2 means, so the depth of the tree is half in every step. So that is the bit of log. Okay. So there are log and number of step. Number of step equals to log n. Okay. Problem is that since it's a 2 for every node, you have 2 elements. Every node. So what is the maximum value of number of elements? N. Number of elements that is possible. 2 for each the number of elements. How many steps you will get? For every step, it increases by यहाँ बटा यहाँ तो एलिमेंट बहुत सारे बॉडी रहता है उनमें और तो आप लेफ्ट डबल 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 हो जाए टू डबल of f of n by 2. and looks like it's works. The 2 is trying to multiply, like make it double. F of n by 2 is trying to make it half. So they're doing like that. If I have 2 of f of n, this 2 is trying to like what are the 3 sizes for O of n? It is only O of n. 2 will make it 2n. Try to increase it, double it, rate of 2. Log of this is trying to decrease it by rate of 2. So overall O of n. Mostly पढ़ाउनु खोजिरहेछ भन्ने कुरा हो कि जस्तो f of n plus f of n minus 1 त यसले O of n छ यसले O of n छ this स्टेपमा यसले n बाट थपिरहेछ दुईटा थपिरहेछ स्टेपमा भनेपछि प्रत्येक इटरेसनमा डबल हुँदैछ divided over n by 2. Answer n by 2 sir. You then log in by other plus log in. So f of n equals to n by 2 plus plus of n by 2. Required to n determine your new n of n neighbor. Wait man. n चाहिँ half हुँदै आइरहेछ हैन Logan. And plus n by 2. And Logan. C plus f 2 f of n by 2. To the power 2 to the power 2 4 8 16 so f of n by 2 means height will be log of n. 2, 4, 8, 16 till a 2 to the power log of n. Which n? So that is n plus 1 in each string, and plus 8 n by n plus 1 second is n by 2 plus 1 second is n by 4 plus 1 third is n by 8 plus 1, right? So it's n plus n by 2 plus n by 4 plus n by 8. Okay. Well, you have to just f of n equals to n plus of n by 2 सारे इसको क्या n जल्दी 1 होगा चलो ऊपर से equals to log n of a to the power n plus 1 minus 1 by r minus 1. A to the power n plus 1 minus 1 divided by 1 by 2 minus 1 n 1 minus 1 by 2 log of n. N log n. 1 by 2, 1 by 4, 1 by 6, 1 by 8, 1 into log of n log 2 base 1. This thing, संख्या 2 2t n by 2 plus c बनेगी t of n equals to 2t n by 2 plus 1. About 3t n by 2 power 3 plus 1 plus 2 plus 2 square sin k equals to 3. Running good. T of n equals to 2 power k, t of n by 2 power k plus 1 plus 2 power k. Condition की होने पर n by 2 के power is greater than equal to n should be greater than equal to k. K होने को log of n. ठीक है? K होने को log of n होना है. जो t का वैल्यू 1 होता है, तो का power log of n बनेगा n plus a to the power log of n plus 1 minus 1 divided by 1 n plus one minus 1 by 1 so by 1 equals to 12 of n.
See this one more example. T of n equal to 2 into t of n by 2 plus n, which means if you do a work of n, work which is proportional to n, if t of n, then the work has to be n. Then we are going to divide the problem into two sub problems, and each problem is of size n by 2. Okay, and this equation is valid when n is greater than 1, and when n equal to 1, the time taken is 1, which means constant amount of time. So let's see the tree method for this. So T of n is, if I do n work, then the problem is going to be divided into two sub-problems, each of size n by 2 and n by 2, right? T is 2, point of n is 4, equation to be n by 2, what's n 2 T of n by 4, right? And now if I'm going to do this one work has to be by 4 work, some way going to reach level work done plus n by 2, which is number of leaves. T of 1 is how many, question is how many levels n in n for n by per one level, but levels should only the lead. So far it works, n into log n, therefore the time
n minus 3 plus n. n छ भने त n ले मल्टिप्लाई नै गरेको भयो हैन, अनि त्यसपछि o of 2 n by 2 र o of 2 n by 2 जतिसम्म जान्छ यो के हुन्छ, दुई गुणाले मल्टिप्लाई भइरहेको है, कतिसम्म जान्छ एकैचोटि पहिलोचोटि n by 2 छ, n by 3 छ, n by 3 छ, त्यही हो n by 2 upon k is greater than 1 है, n is greater than यो चाहिँ n हो Logan.
work done is n, therefore the total work done is n into log n plus 1 k on n plus 0 to n. Now work done is n, then the total work done is n into total number of levels. Now we have to count the total. Let's see how many levels are there. We know that at every level work done is n, then the total work done is n into total number of levels. Now we have to count the total number of levels. Let's see the way in which this the tree is shrinking or tree is growing. Which number of levels. Now we have to count the total number of levels. Let's see the way in which this this is first 2 power 0, and then it is n by 2 power 1. This is first level, and at second level it is n by 2 power 1, and then it is n by 2 power 2, and then it is n by 2 power 3, so on. We are reaching 1, right? So let us say the last level is n by 2 power k. If we levels have k is n equal to 2 power k, it's one level. So if you are having this k, we already know that to log n. N is n. Therefore the total work done is n, and at every level we have seen that work done is n. Therefore the total work done is n into log n plus 1, out of which the leading term is n into log n. Therefore the time complexity is
T and 2 T n by 2. Total number of work done on each level is 2 to the power n.
n log n. So for this problem the time complexity is n log n, right? So that is how this recursion tree method works. We shall see one more example.
Welcome learners to Unacademy Creation. Prepare for GATE 2025, then you can go for 30 months Adra CSIT subscription, where you will get Ravindra Babu Ravulla recorded videos completely.
Oh, okay. It's 2 hours, so let's take a break. We haven't even started it. I was just so confused with the time complexity of the recursive function. I thought we could come up with some kind of solution, find it pretty quick, but I couldn't. It seems like I have to do but I think that's not bad that making an equation till n equals k equals to 3. And when you start to seeing the trend, you can make an assumption that like, because we don't need to be very exact with the answer. Yeah. Okay. See you after 10 minutes.
And that might be a reasonable trap to fall into because we know that in the long run, we're going to have to evaluate to
Uh, okay, let's start, baby. No, uh, integrated webcam. Okay.
2 to the n function calls. And so I guess that means we have to put 2 to the n function calls on the stack. But there's actually some nuance to this. The time complexity of this is not the same as its space complexity. So let's jump in. Let's say that we made our top level call to dibb of 5. We know that that is added to the stack in the same way 5 calls 4, so it's added to the stack. And we add a stack frame for every call that we make down until just the base case, right? So at this point, I reached a scenario where I have a base case and I'd have about 5 stack frames. It's not that this time has a 2 to the n time complexity. Awesome. So we identified this dibb function as having a 2 to the n time complexity, but what do we know about the space complexity over here? I think a common mistake I've seen people make is kind of automatically assume that the space complexity of a recursive function will be the same as the time complexity. And that might be a reasonable trap to fall into because we know that in the long run, we're going to have to evaluate 2 to the n function calls. And so I guess that means we have to put 2 to the n function calls on the stack. But there's actually some nuance to this. The time complexity of this is not the same as its space complexity. So let's jump in. Let's say that we made our top level call to dibb of 5. We know that that is added to the stack in the same way 5 calls 4, so it's added to the stack. And we add a stack frame for every call that we make down until just the base case, right? So at this point, I reached a scenario where I have a base case and I'd have about 5 stack frames on my call stack. And the important insight is when we actually hit this base case that I've highlighted, the left one over here, it actually will return. When something returns, when a function returns, its stack frame is actually removed or popped from the stack. And at this point, only after I have returned from that left one would I actually add the right one to the stack to be explored. And this process continues. Notice that at any point in time, the most number of stack frames that we use up is exactly 5, right? It's not as if we throw all of these function calls on the stack at once. And because we have such a nice tree visual, we know that the number of stack
Actually, stack is
frames that we're ever going to use is really just the height of the tree, right? So the height of the tree is n, like we said before. That means our maximal stack depth is also n. So we have n space complexity coming from the call stack. So overall, for our dibb function, we're looking at a 2 to the n time complexity, but only an n space complexity. All right, so let's look at one more function, 2 so n. So we have n space complexity coming from the call stack. So overall, for our dibb function, we're looking at a 2 to the n time complexity, but only an n space complexity. All right, so let's look at one more function. Say I gave you this very similar lib function. Notice that in its recursive calls, it does an n minus 2. So by now, you should be able to visualize what a structure like this would look like. Say we initially called lib with a value of 8. What would the full tree look like? Children, but this time we go by 2s, right? So if I look for some familiar ground here, I notice that from one node to the next, I do a minus 2, and this occurs all the way down to a base case. So we already know that, hey, we can identify this tree as having a height of about n over 2. So to the next, we double. Know that, hey, we can identify this tree as having a height of about n over 2. So I guess that means that the time complexity is going to be 2 to the n over 2 power, right? Because from one level of the tree to the next, we double the number of nodes. So that's that 2 times 2 times 2 repeating pattern for the number of levels, and our number of levels is n over 2, right? However, we can actually simplify this time complexity. We can take that n over 2 in the exponent and simplify that to just an n. So overall, we're looking at a 2 to the n time complexity. And using our same arguments from last time, we know that the space complexity for this from the stack is also going to be n over 2, which simplifies nicely to n space complexity. So we see that overall for our lib function, we're looking at a 2 to the n and fit in this picture. Space complexity. That being said, where does our original Fibonacci function fit in this picture? Well, you could imagine a recursive column. So in a sense, it's kind of like smack in the middle, right? If you let me abuse the notation a little bit and just talk, I already plugged in some values, right? We know that, hey, the lower bound is max 1, like dib did, but its second recursive call is n minus 2, like lib. So in a sense, it's kind of like smack in the middle, right? If you let me abuse the notation a little bit and just talking about the time complexity, you can kind of say that the complexity of fib is somewhere between dib and lib, but we've already plugged in some values, right? We know that, hey, the lower bound, that is dib, has 2 to the n, and the upper bound, that is lib, has 2 to the n as well. So and its evidence is, of course, these fields. You can kind of imagine numberfully a's, but exactly this, right? For. So take a moment, look at this tree. The tree is a similar left-hand side, one that we ran earlier, and it's some duplicates. So forward bonus exponent. With that being said, let's go ahead and get to the punchline on this fib function and work on optimizing this solution. All right, now that we discussed a plan, I think we're ready to actually implement some code that will actually carry that plan out. Here time memoization. So I have a nice, and so what I can do for my existing fib function is I can kind of just bake in some optional arguments. So this syntax and JavaScript argument by, right? So that's going to be useful that way. Whoever is, I want to do be the first thing I return the value that corresponds to that memo's key, right? I'm just using the original argument n as a key in my memo. And this condition is really just some classic JavaScript syntax. Maybe you haven't seen of Alvin, that's me. Then it had an object, true. Complete the original return. So any return, that value calls are added here to fib, right? Second arguments, and so they're actually going to receive the same memo object, and it would be like passed by reference, right? Because when you pass a JavaScript object to a function, you actually receive kind of that exact object, right? You don't receive a copy of it, which is really neat. So basically, I'm giving my function calls a way to sort of communicate to each other. They all have some sort of global information to reference across other recursive trees. So this code is looking good. Again, I just want to emphasize, I only added a new argument over here. I added a new base case on line 5. Let's go ahead and run. And the 50th head back to the drawing board and really understand, what happens when we execute this sort of code. All right, so it looks like we implemented the improved version of Fibonacci by memoizing it, and it's how the shortening the program that we definitely had an impact on the time complexity. However, I really want us to understand, how the structure of the recursion tree changes once we implemented this memoize. Really, what I'm looking at not do this. So by doing a calls, right? Okay, so all plus one at my memo, Fibonacci to value to also make the endpoint added memo, value in my memo, right? And a tree recursive calls. It's evident that by memoizing our Fibonacci function, we definitely cut down on the number of recursive calls. We wanted to visualize that. We ended up with this kind of structure. Here in a light blue, I have circled the nodes that we technically didn't need to do the full recursion at, right? So these nodes of 2, 3, and 4, for the small example of my initial fib of 6, I was able to kind of fetch a value from my memo and kind of forego traveling down the recursive subtree. So what do we actually know about the time complexity of this function now? Well, I think it's really important that we always try to, this is the same tree, let's say I kind of tidied up a little bit. So I know that in general, fib of 6 kind of has this structure. So I want you to take a moment, look at this, and in your brain, picture what fib of 7 would look like. If I memorize fib of 7, what would its subtrees look like? Well, it would really just look like this. Notice if I root myself at the 7 node, its left child is still 6, right, minus 1, and its right child is still 5, minus 2. So this still looks like this. Okay. If you're not convinced by, that just like structural argument, let's say we were a little more methodical. Problems or new path of this chain. I go 9, 8, 7, 6, 5, 4, 3, 2, right? So this goes all the way down in a very, very, very linear fashion, right? Just counting down initial top level call. So I know that what I have highlighted in yellow is just a linear chain, right? There are exactly n nodes, but I haven't accounted for everything in this picture, right? Some of the nodes are still in white, meaning I need to kind of work them into my description of what they're kind of paired off in a way, right? And edge. So overall, the number of nodes simplifies to n as well. And this is pretty powerful stuff. By memoizing our fib function, we brought it down from an exponential time complexity to just a Fibonacci. And what we'll do is work on a more involved problem. This one has more of a narrative to it. So say that you're a traveler on a
Say that you are a traveler in a 2D grid. We begin in the top left corner. You're right, eh? Top left corner button.
two-dimensional grid. You begin in the top
जस्तो मान्छे टप लेफ्टमा छ होइन, यो गोल इज ट्राभल टु द बटम लेफ्ट कर्नर. You begin in the top left corner and your goal is to travel to bottom right corner, down or right. अब यसलाई त रिकर्सिभ तरिकाले गर्न मिलिहाल्छ. सबै तरिकाले चाहिँ एउटा त होइन, एउटा जस्तो के भयो भनेपछि फङ्सन minimum step certain position. So you are somewhere. If your position equals to ending position, written steps. Okay. If your position equals to right end, go down. That is minimum step equals to your position plus down step plus 1 into 1 more step. Equals to bottom end position plus 1 step right, and this is a step plus 1. Otherwise, return minimum step up position plus right. No. Position plus right, comma step plus 1 or minimum step up position plus down step plus 1. Okay, it doesn't check for the age condition. If okay, so it will take, so at any step it can take 2 steps. So it's 2 to the power n. What do you take? But it can be linear time if we do memoization. Okay, one of it is We can also do dynamic programming in this, I guess. Great travel. यो त lead code में पनि होला नि. Great travel. Great travel. Oh, there is a robot on M, N मा robot छ अरे हैन. The robot is in the top left corner मा छ हैन. के हो? एन्सर छ त के हो? Unique path M र N equals 0. को लेखेको यो कोड? सल्भ गरिसकेको इक्वेसन? कसैले विकसित तरिकाले सल्भ सबमिसनको हिस्ट्री हेर त. Number of all possible way. भनेको त जस्तो यहाँबाट यहाँ जान सक्छ, यहाँबाट यहाँ जान सक्छ हैन. यहाँबाट यहाँ जान सक्छ, यहाँबाट यहाँ जान सक्छ भन्यो हैन. एउटा पोसिबल वे यो भयो, एउटा पोसिबल वे यो भयो, एउटा पोसिबल यो भयो, यो भयो. पोसिबल वे भनेको त सबै ब्रान्च कोडलाई जोड्दै जानु होइन त नि. हैन. नम्बर अफ मिनिमम वे भनेको हैन. यहाँ भइरहेको सबै मिनिमम निकाल्नु भनेको म्याथ डट मिनिमम हैन. नम्बर अफ पोसिबल वे भनेको सबैले जोड्दै जानु त नि. Oh man, my brain is not working. I need to be very active because I have to be very, very active. Math dot minimum learning. जस्तो छैन ट्रीको अल पोसिबल वे के छ भन्नु भने यसको भ्यालु यहाँ पठाऊ. दुईटा भएन. यसको र यसको टोटल ब्रान्च जोड्ने तरिका भनेको सबै फङ्सन कललाई जोड्दैन म. माथि जाँदाखेरि जोड्दै हो कि. धेरै सोच्दैन. म तीनटा लाइन सोचे. जस्तो यहाँ सर्टेन पोजिसन. ब्याकमा जान मिल्यो, डाउनमा जान मिल्यो. यता गयो, यता गयो. सोल्युसन के हो मतलब चाहिँ जोड्ने त हो नि. यसले के भनेछ मेमोराइजेसन. यसले फंक्शन में ऑब्जेक्ट बनाएर पठाएको छ This is tough for now because I'm gonna go down in the cold and torture me for a few minutes, so that's fine. I could feel fresh. See you.